Okay, we are going to go to chapter 15 and talk about solutions. Um, so let us get going on that. So solutions are really the substances that end up with the aqueous symbol next to them. And as we might have talked about previously, there is a difference between aqueous and liquid. And when you have liquid, usually that's a pure substance. Like something like water, which would be in the liquid state. Now, something that's aqueous, that is a solution, it really is a homogeneous mixture, and homogeneous mixtures are at least two of something, and they do look the same throughout. Everything mixes really well. And if you were to take, for example, our water and mix it with some solid sodium chloride, the sodium chloride would dissolve in the water part. And together that would get you basically a sodium chloride solution that would get the aqueous symbol next to it. So again, a liquid is usually just a pure substance by itself, really nothing mixed together. Bless you, a solution is usually something that is mixed together. When we talk about solutions, there's really two parts to a solution. There is the solute, which is the smaller part of the solution. That is usually the substance that's being dissolved in the larger part of the solution, which is the solvent. So in our above example there, water and our sodium chloride, water would be our solvent, and water is a really good solvent, as we'll talk about, for a lot of things, including ionic compounds. Water oftentimes is a solvent, but it is not always a solvent. So water in certain cases, as we'll talk about, could be a really bad solvent, but in a lot of cases it's really good. That would make the sodium chloride our solute, and again, these guys are going to make our sodium chloride solution. How do you know what is the solute? Well, usually the name of the solution is the solute. So if you have a sodium chloride solution, sodium chloride is your solute. If you got like a potassium fluoride solution, then potassium fluoride is your solute. If it is ionic, probably a really good chance that water is going to be your solvent. But again, water doesn't always have to be the solvent in that particular case. Water is a really good solvent because it is polar. And when we have water, because it is a polar molecule, it really means it has a positive side and a negative side. And in the case of water, the negative side is near the oxygen. The positive side of water is by the hydrogens. And that works really well with a lot of ionic compounds. And that's because it could do what is sometimes referred to as a ion dipole interaction. And that is a fancy way of saying basically the water molecules will surround the ions and it will use intermolecular forces, which all intermolecular forces are basically a simple idea of opposites attract to each other. So the negative side of one compound is going to be attracted to the positive side of the other compound. And that's basically how all intermolecular forces work. Intermolecular forces, again, are the forces that hold one molecule together with another. It could be the same molecules, it could also be two different molecules, how they interact. So what happens when we do dissolve something like sodium ion, which is positively charged, and chloride ion, which is negatively charged, when we dissolve it in water, what ends up happening is water will surround the positive ion, actually using its oxygen side to do so, because the oxygen side is more negative, and it would be attracted to the positive ion that's floating around in that solution. And for the negative ion, it also gets surrounded by water, but it's actually surrounded by the hydrogen part of water, as that is its positive side. And those interactions there, it allows two things to really happen. It allows a solid like sodium chloride to dissolve, and a reminder that it is a physical change, even though we cannot see it anymore. And the reason we can't see it anymore is there is a lot of water molecules basically surrounding all these ions. And because there's so many water molecules surrounding the ions, it no longer is visible to you with your naked eye that those ions are still floating around in that solution. Sort of disappears, if you will. Thank you. Now, this type of interaction is definitely a physical change, because if we were to again sort of heat up this solution of salt water, we can evaporate off the water, and that's going to that's going to allow those ions to come back together. Now, what do we do when we do dissolve it? We kind of help this along a little bit. We stir it, which throws a lot of water molecules on the solid. It also provides some energy, which allows those water molecules to pop off the ions from the solid. Before we do that, all the solid is basically organized in a really ordered sort of fashion, and that's able to sort of pop it off because there's just so many water molecules that are present. This process is what is called sometimes hydration. And this is really what it is when you write something like I have a sodium ion in an aqueous solution floating around in the solution. That's basically what's happening is, again, that sodium ion is really not by itself. It's surrounded by several waters at all times, and that's what's keeping it floating around in that solution. Again, as I mentioned, if you decided you wanted to heat up this solution of salt water, when you would do so, the water part of it would actually evaporate off. It just needs to get to like 100 degrees, and you'll start evaporating off all these water molecules, and they'll all go away. And at that point, there's really nothing stopping these two ions from coming back together. And it's kind of like, again, those earlier experiments you did this semester where you put your solution in the evaporating dish, you heated it up, and you're left with this like residue that's left over there in the evaporating dish. And again, that's all the water basically leaving. Those ions now can come back and stick together. Remember, the attraction between the ions, the electrostatic attraction, is a super strong sort of attractive force, one of the strongest forces you could have. It's just sort of overtaken by the amount of water that's present that keeps them basically apart. Any questions on that there? And here again is what we see. We have our ionic solid here. Water's coming in basically and plucking off our solution, our ions.
An ionic solid dissolves in water because of its polar nature. Notice how water molecules become attached to the ions of a sodium chloride crystal in the process called hydration. Positively charged sodium ions attract the partial negative charge of the oxygen in water. A similar attraction occurs between negatively charged chloride ions and the hydrogen atoms, which have a partial positive charge. These interactions loosen the attractions between the ions in the crystal, dislodging them from the crystal. Additional water molecules surround the released ions, insulating them from attraction to other ions.
So again, you can see it's pulling those off, and you help it along by obviously stirring it. Obviously here, remember that the larger circles are probably our chloride. As it's gained electrons, became larger in size. The smaller kind of green circles there are our sodium in this case, which have lost electrons, shrunk in size as it has lost some electron density. This is really, sort of the reasons why we see certain things happen when we look at different types of bonds. Ionic bonds, as a reminder, right, it's always between a metal and a non-metal. And again, we get that opposite attraction that occurs as electrons always go from the metal to the non-metal, creating our ions. When we have covalent bonding, that's a little bit different. Again, as we talked about, that's between two non-metals. We have sharing of electrons. And in the case of that, we may have sharing of electrons that are equal, which creates a nonpolar bond, which is essentially neutral, right? There's no positive side, there's no negative side. And we can create a polar bond where there is a separation of charge. Remember, it is the electronegativity that allows us to do that, to create that sort of difference. And anywhere when we do a difference in electronegativity of 0 to 0.4, remember that is considered really a nonpolar covalent bond, equal sharing of electrons. And when we get that difference in electronegativity of, like above zero point 0.4 to below 2, that is some type of polar bond. And it's really in the case of sort of covalently bonded atoms are molecular molecules, the presence of certain types of bonds, which plays a really big role in terms of, for example, whether or not something would be soluble in something else, or if there's going to be any type of interaction. So as we will see and as we'll talk about, you can have some molecules that have kind of like two parts to the molecule. It has kind of like a nonpolar part and it also has a polar part. And because it does have a polar part, it does allow it certain types of interactions it could do that if it didn't have that polar part of the molecule, it would not be able to sort of accomplish. So when we talk about things that are soluble in water, any ionic compound is definitely going to be soluble in water. So that's almost a automatic. If you have an ionic compound, you're looking for something to dissolve it in. Water is probably your good choice there. It's going to be a really good solvent for anything that's ionic. But we also see things that are non-ionic compounds that are also soluble in water. For example, sugar and ethanol. If we were to draw ethanol, it looks something like this. And when we look at ethanol, it actually kind of has two parts to it. We have kind of this part of the ethanol molecule, which is essentially all carbon-carbon bonds and carbon-hydrogen bonds. And essentially that is all nonpolarness happening there. The bond between carbon and hydrogen is nonpolar. Definitely the bond between two carbons is nonpolar. But what ethanol does have is a second part of it, which is right here, this bond. And this bond actually is a polar bond. And it's actually the same bond you find in water, oxygen being more electronegative, it's more negative on the oxygen and more positive on the hydrogen. And what happens in this situation is because ethanol does have this kind of group is referred to, this OH group, it is able to participate pretty well with water, which also has pretty much the same group there, positive, negative, right, happening. And it allows something like ethanol and water to bond to each other through opposite sides there, positive side of one, negative side of another. This is what is known as hydrogen bonding. And hydrogen bonding is a strong intermolecular force. Remember, to be able to hydrogen bond, you need to have a bond between hydrogen and nitrogen, oxygen, or fluorine. So in order for somebody to have the ability to actually hydrogen bond, it does need to have a hydrogen directly attached to one of those three elements. And that's what we see here in ethanol. We have a hydrogen directly attached to oxygen, which allows it to hydrogen bond. And it again is the same thing we see over here in water. Now, a reminder that not all hydrogens can hydrogen bond. So even though this guy has all these hydrogens, none of those hydrogens are directly attached to nitrogen, oxygen, or fluorine, and they are nonpolar and they cannot hydrogen bond. So just simply having a hydrogen doesn't guarantee that you get hydrogen bond. That hydrogen does need to be connected directly to nitrogen, oxygen, or fluorine. Now, this sort of molecule here, which is in organic terms referred to as an alcohol because it has that OH group, solubility does change depending on the molecule. So even if a molecule, for example, like what we see here, has a polar group and can interact well with water, what happens, for example, is if we increase the number of carbons present and hydrogens, by the way, these are all going to be hydrogens basically. What happens in this case is we now have a fairly large part of this molecule that's nonpolar. So we get this really big nonpolar part. It still has this part here that is polar. But what happens in this case is because this molecule now became pretty big, and basically that nonpolar part gets in the way of the interaction between water and the OH group that's on it. And it's what's sometimes referred to as steric hindrance. Basically, this big nonpolar part prevents this part from reacting well with water, and they really don't mix really well. And this thing would probably have no solubility here because of that. And usually when you look at organic compounds like these that have carbons, hydrogens, maybe an OH group or something on it, usually when you hit about 5 or more carbons in that type of molecule, the solubility drops to almost nothing. But before that, if you go like up to like 5-ish sort of carbons, like ethanol, like methanol that has 1, they are relatively soluble in water, but the solubility definitely starts to decrease a lot as you build out those carbons and hydrogens in that nonpolar part. Remember that in order to get something to dissolve in water, you basically have to replace water-water interactions with similar type of interactions. Water is a relatively small molecule, so you try to park this guy in the parking lot there with all the water molecules, it's not going to fit really well. It's just too big to kind of work in there. Now, what about sugar? We do know sugar dissolves obviously in water, and sugar is a relatively larger molecule. But one of the things that sugar has going for it is, if you look at it, there is a bunch of OH groups basically all around sugar. And everywhere there's an OH group, that gives water an opportunity to interact well with sugar. It makes it really soluble in water, even though it's a little bit larger of a molecule. That's one way you could actually increase the solubility of something in water is if you had something that had multiple OH groups, it'll actually make it a little bit more soluble than just if it had one OH group present because it's able to basically hydrogen bond. So here's our methanol, which is an example. Again, it's got this OH group, negative here, positive here, hydrogen bonding between those two, going to make it really, really soluble. There's our ethanol as well. So what about oil and water? Do they mix? They really don't mix because in the case of oil and in the case of water, oil really is just a long old chain of just carbons attached to carbons, and to those carbons, hydrogens attached. And basically oil is nothing more than hydrocarbons and nonpolar, like I said, pretty much nonpolar. So the problem with when something like oil wants to kind of play with water or mix with water is they are using very different intermolecular forces. So nonpolar molecules, their go-to for intermolecular forces are dispersion forces. And dispersion forces are pretty much your weakest type of intermolecular force. They rely upon something happening like electrons being kind of dissociated and moving around. They require somebody to come near them that has a charge, and they're very, very weak. And that's very different than as we were talking about here with water. Water definitely go to sort of intermolecular force is hydrogen bonding, and it is going to want to do that. So over the long period of time, they cannot interact really well. They cannot maintain that interaction, and they will eventually separate apart from each other. So kind of like if you take some oil and vinegar salad dressing, you mix it up really well, it will mix for a bit, and if you leave the bottle just sitting there, eventually what will happen is everybody will kind of separate out from one another, again, because they cannot over a long period of time maintain that interaction as one's trying to do hydrogen bonding, one's using dispersion forces. That is not going to mix. So when we think about will something be soluble in something else, what we're thinking about is, do these two things basically use similar intermolecular forces that they use with themselves that they again could use with somebody else? So remember, hydrogen bonded dispersion and dipole-dipole interaction are all three intermolecular forces that are used. Again, this is our strongest This is our weakest. And that means that when we think about like dissolves like, things are soluble if you try to mix together something that's ionic and polar. You're not going to have any problem. It'll be able to do kind of like what we talked about sodium chloride. If you take something that's polar and polar, you're going to be in good shape. If you take something that is nonpolar and nonpolar, you also will be in good shape. They both will use dispersion forces and they'll be able to interact well with each other. Now, you only really kind of run into problem when you try to cross over there and you have something that's insoluble, and that is when you take something that is polar and nonpolar that typically will not mix with one another. In addition, something that's ionic and nonpolar will not mix really well with each other either. So if you had a nonpolar sort of substance and you want to mix it with something, water would be a terrible sort of solvent to use because water, again, is going to want to use hydrogen bonding, which is very, very different than that. Nonpolar guy is going to want to use dispersion forces, and they really will not mix together. They will eventually end up layering out, if you will, and you'll have some different layers sort of happening based on that. So here's our sugar molecule, and as I mentioned before, you can see there's just a lot of OH groups all over it. And again, everywhere there is that OH group, it's going to give it a place to interact well with water. Down on the bottom is pretty much oil. That's how they get things like gas and stuff like that. They crack that thing in half. They break it into smaller pieces, and it gives you things like gas. Gives you things like, maybe sometimes waxes and stuff like that, depending on what you're doing. This is typically what we do see, and we do see an oil layer. Usually the organic layer is up on top, and the water or aqueous layer is usually on the bottom when they mix. That is, maybe you remember a while back at the beginning of the semester, you did those halogen ones, experiments where the halogen jump layers and the top layer changed color to a different layer. That was the same idea. You used something like heptane, I think, and we had an aqueous layer, which was our salt solution, and something like chlorine water, bromine water, iodine water in the top solution. Now, when we talk about things being soluble, if one substance does dissolve in another, it is considered to be soluble. Salt is soluble in water. When two substances really don't mix, they are said to be insoluble in each other. Oil is insoluble in water. There usually is a limit to the solubility of one substance in another. For example, if you're doing something with a solid in a liquid, oftentimes that is also temperature dependent. And if you have a solid and you're trying to get it to dissolve in something like water, for example, usually if you kind of increase the temperature, that usually will allow a lot more of the solid to dissolve. And vice versa, obviously, if you lower the temperature, it actually will let less solid dissolve. Gases are usually soluble in one another, and that's just because gases, by their nature, if they're in a container, they are flying around, which means they are constantly mixing with one another, and they would be soluble. Some liquids are, again, also usually soluble in each other. So that list that we just did there, if you got polar and polar, you're good to go. If you got nonpolar and nonpolar, you're good to go. But again, if you cross over polar to nonpolar substances, they are not going to mix really well. Some other sort of properties that we see in terms of solubility, solubility of solvent does depend on temperature. So again, like I mentioned, the larger the temperature or higher the temperature, you have a greater solubility of that solid in a liquid. Also, gases in a liquid are dependent on the temperature. At a lower temperature, if you had a gas molecule in a liquid, at a lower temperature is going to be flying around slower, which means it's going to stay dramatically drawn here in the liquid part much longer before it escapes because it's not moving around as fast. Obviously, vice versa, if you had a higher temperature, your gas molecule is going to probably be able to jump out of the liquid a lot quicker and escape. When we talk about gases, it also depends on pressure. The higher the pressure, typically, the more soluble a gas is in a liquid. The classic Henry's Law example, which is your soda can, before you pop the soda can open, you have a bunch of water and a lot of CO2 molecules basically dissolved in the water part of your soda. When you pop your soda can, obviously it's under pressure. You just release the pressure, and what that does is it allows these CO2 molecules to escape the liquid portion. That is the fizzing you see come out of the top of the can, right? When you pop it open, it's all that CO2 molecules basically coming out because you also gave it an escape route of your can. Air is here, which will blow those CO2 molecules away. And as you might know, right, if you leave a can open that's carbonated, eventually you come back in and it is flat, right? Because all the CO2 basically escaped, got blown away, and now you got basically just syrup water sitting in your can at that point. And again, obviously, before you pop the can, much higher pressure. That's what keeps the CO2 bubbles basically in the water part under that, because at a high pressure, you have a small volume. Now, when we talk about ways to classify solutions, we could have a saturated solution. And a saturated solution is a solution where you have basically hit the point where all of the solid that you're trying to dissolve will actually dissolve at that given temperature. You basically hit the maximum point at that temperature where solid will dissolve. And if you're right at that saturation point and you've hit it and you continue to add more solid, it will not dissolve. It basically will just start to pile up at that point unless you do something like increase the temperature. Now, before you get to that point, you have what is known as an unsaturated solution. And an unsaturated solution is a solution that really hasn't hit there. That means that you can still dissolve more solid in an unsaturated solution. You could continue to dissolve solid in an unsaturated solution until you hit a saturated solution. So you can continue to dissolve that solid. It will continue to dissolve, no problem, until you hit that saturated solution. Again, at that point, no more will basically dissolve. Now, there's a third type of solution, which you probably saw the other week in the lab, and that is a solution that is known as a supersaturated solution. And a supersaturated solution is basically usually made, for example, you take a solution, you're trying to dissolve some solid in it, and you heat it up. And as you're heating it up, what's happening, because solubility is based on temperature, you're going to be able to, at this hotter temperature, as you're heating it up, get a lot more solid dissolved in it than you would at room temperature. So as you're heating this up, you're going to be able to basically dissolve a lot of solid into that solution. And then typically what you do is afterwards, you let it cool down pretty much undisturbed. You don't really want to touch it. And what happens is as it cools back down, the solubility changes of that solution. So as you were heating it, the solubility was really high for whatever you're dissolving. But as it cools back down, the solubility changes. The problem is at this point, you've already dissolved all your solid in there, and it is a liquid at this point. But it's a very unstable liquid at this point because of that. And it's so unstable, as you probably saw maybe in that demonstration, if you just took one little, barely could see it, piece of whatever you dissolved in there, solid, and you drop it into the solution, that is enough to basically to tip the solution over the edge, and all of the solid, you could actually see it start to come out of the solution, and it will go from a liquid to a solid, rock hard sort of solid in that case. For example, when you do that one in the lab, sometimes if you don't even get to the crystal part and you just kind of put it down too hard, that is enough to cause it to actually come out of solution really, really quickly. It should have been experiment 20, first part, I think, is what you saw that maybe. So to see a sort of animation of that should be similar.
Saturated solution of sodium acetate in water. A small crystal of sodium acetate will be added to the solution.
So it's already a supersaturated solution. It's been heated. It's been cooled back down.
Attention of the portion of the solution to which the crystal is added.
It has way too much dissolved in it, and you just put one small thing, you can barely see it, And again, that is, again, all the solid coming out of solution. And it's going to go from obviously the liquid state to the solid state and also give off some heat in this particular one as well. And it'll be rock hard. Super slow motion replay, please. So,
Here is the process again in slow motion.
there it is. Like, so that is a super saturated solution. Again, it's a very, very unstable solution because basically you just kind of got all that stuff dissolved and then changed the parameters by lowering the temperature, changing the solubility, and it just needs a little push over the line there. Any questions on that there? Other ways you could describe a solution is concentrated or dilute. If you have a concentrated solution, you'd have typically a relatively large amount of solute in it. And usually we buy our solutions more concentrated, and then we take them and we dilute them down usually to use them. And a dilute solution contains a relatively small amount of solute. Concentrated solutions are sometimes referred to as stock solutions. And we take those, and again, like I said, usually we'll add some water or something solvent to it and dilute it down. If you look at the molarity or the concentration of solutions with the big M next to it, the larger the M value, then the more concentrated it is. The smaller the M value that you see on bottles in the lab, the more dilute solution it is. So let's talk about actual concentration units and some calculations. The first type of concentration you're going to talk about is mass percent. It's sometimes abbreviated percent M/M. It is the mass of the solute divided by the mass of the solution times 100%. Now, the important part of this calculation is actually the bottom, and that is the mass of the solution. So a reminder that the solution is made up of two things. It is made up of the solute and also the solvent. And you want to make sure that you actually add those together because I would say probably more so than other problems, when you come across a mass percent type problem, they very commonly like to separate those values out. So they'll give you the mass of the solute, they'll give you the mass of the solvent, and it's a very common mistake. People will just divide by the mass of the solvent and not actually add those together. So you want to make sure that you do that. Another way that you could kind of use this percent mass to mass or percent concentration sort of usefully is, let's just say you had a 4.5% by mass sodium chloride solution. Now, sometimes we may want to take a more dimensional analysis approach in our calculation, and you basically could turn this percentage into a conversion factor. And as you might be familiar with, right, typically if we want to kind of convert a percentage into a usable sort of conversion factor, 100 is typically what we think about. So we could turn this into a conversion factor, and that would mean that there would be 4.5 grams of sodium chloride in 100 grams of solution. So that is sort of a conversion factor that you could get from the actual percent mass to mass. And because that's a conversion factor, you could flip it around the other way and go 100 grams of solution is 4.5 grams of sodium chloride. So you can take more of a dimensional analysis approach. You could use the percent mass to mass if it's given to you as a conversion factor. You absolutely could still plug and chug into this equation and you will get the same answer. But again, if you're afraid that maybe you might rearrange the equation incorrectly, remember that one of the benefits of doing your calculations through dimensional analysis is you don't have to worry about the math part of it. Just opposites cancel, and all you have to remember is multiply the top right, divide the bottom, and that will take care of the sort of math part of it, and you might not rearrange it incorrectly. Now there is also, and by the way, this would be usually grams divided by grams is sort of the units that we use here. There's a couple of other percent concentrations that we come across. This is percent volume to volume, like percent volume in alcohol type of thing. And this is equal to the volume of solute divided by the volume of solution times 100%. In this case, usually it's milliliters, and milliliters is typically the units we kind of roll with. We also have percent m/v, which is mass to volume. And that is the mass of the solute, which is usually grams, divided by the volume of solution, which is usually milliliters, kind of like a density almost, times 100% in this case. Now, once again, much like the percent mass to mass, if you're given the percentage of either of these, you could also turn them into conversion factors. So if you had 4.5% by volume sodium chloride solution, that would mean you have 4.5 milliliters of sodium chloride and 100 milliliters of solution, or in 100 milliliters of solution, you would have 4.50 milliliters of sodium chloride. So again, you could kind of turn it into a usable conversion factor. And same thing with the guy on the bottom. If you had, using the same number here, 4.5% mass to volume sodium chloride, that would mean that you have 4.5 grams of sodium chloride in 100 milliliters of solution, or in 100 milliliters of solution, you got 4.5 grams of sodium chloride. So again, you could kind of turn these into conversion factors. Like I said, take a more dimensional analysis approach, or again, you can just plug into the equation, obviously, and solve for whatever you're looking for. Any questions on those there? All right, let's try one here. A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. Calculate the mass percent of calcium chloride. Okay, let's take a look. So here, obviously, we're going to calculate the mass percent. So we'll go with our equation here. Our mass of our solute divided by the mass of our solution times 100%. So when we look at this here, we have 2.5 grams of calcium chloride. That is going to be our solute. It is the smaller number, or the smaller part of this solution. Our solvent is actually going to be the water in this case, and we got 50 grams of water, which is our solvent. So again, as I mentioned before, they oftentimes will sort of separate those two. So you do need to add them together to make sure you actually get the mass of the solution. That's going to be 52.5 grams is our mass of our solution. We now have everything that we need. We could go into here. Percent mass to mass is going to be 2.5 grams divided by 52.5 grams times 100%. Again, we don't want to divide by just the 50, which is the solvent by itself. And that's going to get us 4.76%. And you could leave it as percent m/m. And you could put something like calcium chloride down and give us our percentage in this case. Any questions on that one there? So again, like I said, very common error. People just kind of go with the solvent. Yeah.
Oh,
Yeah.
do we do sig figs for the percent, or do we just always get the numbers?
Yeah, no, you should probably do, you could do sig figs in this case. We ended up with basically 3 and divided by 3, so 3 sig figs would work out. Other questions? And obviously here we were adding, so we went to smallest decimal places to get there. Yeah. All right, let's try another one here. Concentrated hydrochloric acid contains 37.2% by mass HCl. What is the mass of HCl that's needed or contained in 35.5 grams of a concentrated HCl solution? Okay, so here again, we're dealing with percent mass to mass. And in this particular problem, we're actually given the percent mass to mass, which is 37.2%. We're looking for the mass of our HCl, which is our solute. And we have the mass of the solution, which is 35.5 grams. Now you may be asking, how do I know 35.5 grams is the mass of the solution? I know that because they're asking me to solve for the mass of the HCl. And remember that, as we talked about, pretty much the name of the solution is the solute. So if you have an HCl solution, HCl would be your solute. So if you're looking for that, that is how I know I'm looking for my solute. I again could just plug it into this equation and solve for what I need, which is this, and actually solve for that. But again, I'm going to take more of a dimensional analysis approach to this calculation. So that 37.2 means I have 37.2 grams of HCl and 100 grams of solution, or 100 grams of solution, I have 37.2 grams of HCl. So starting with my grams of solution, again, by taking this sort of an approach, I don't have to think about rearranging that equation, just opposite cancel. So that's going to do it for me there, 37.2 grams of HCl, 100 grams of solution. And because I did the dimensional analysis, I know I multiply and I divide. So that takes care of the math part of it for me. The grams are going to cancel, and that's going to give me something like maybe 13.2, I think. Once again, if you did decide to just plug it into the formula, it's perfectly fine. You're basically going to be doing the exact same math as we just did there. You would basically be multiplying everything across there and end up with the same math. Any questions on that one there? Yeah. Then let's talk about probably the most important unit of concentration, which is molarity. And molarity is capital M, and it does stand for moles of solute, liters of solution. And you can think of molarity as sort of a formula, if you will, like density. Molarity is moles divided by liters. Liters would be moles divided by molarity. And lastly, moles is equal to liters times molarity. I would say that it's very common that you solve for any of those three. You very often can solve for the volume, you can solve for the molarity, and you could also solve for the moles. Now, when you are using molarity, I would highly recommend that you get rid of the big M when you're doing calculations. So for example, if I had 4.5 molar sodium chloride, you should really not use this in your calculations. Take a dimensional analysis approach, and you could actually use the molarity as a conversion factor. And what that means is 4.5 moles per liter of sodium chloride. You could also flip it around and go a liter on top, 4.5 moles of sodium chloride on the bottom. The number always stays with the moles part, and it's always 1 liter. The reason I highly recommend you get rid of the big M when you're doing calculations is most of the time people don't even know what that means, the big M. They don't even know about the volume. They're not sure where the liters are, if there even is liters or milliliters. I would say most of the time people, when they see the big M, all they think about is like moles or something, because they see M's, they think moles. So it's a really good idea to get rid of the big M, put both of the units. The good idea of that is you might actually see the unit and remember that you do have to do something with the volume part of it. It's also really important that when you do this calculation, that you do convert your volume into liters before you multiply it by the molarity. That way you can take liters times moles per liter. Liters cancel and gives you moles. You do not want to multiply molarity by milliliters. Not that you can't do that, but it will not give you what you probably are thinking you're going to get, which is moles. You will not get moles if you do that. If you take milliliters times molarity, you don't get moles. You actually get what are known as millimoles, which are like moles but 1,000-fold off. Yeah. So in most calculations, you actually need moles, not millimoles. So always make sure if you're using molarity by itself that you do convert it into liters before you multiply it so that everything works out right. To be truthfully honest with you, molarity can be thought of as millimoles divided by milliliters, which is why sometimes people will multiply by milliliters. And that's because the milli on top and the milli on the bottom will actually cancel, and you're back to moles per liter, and you have basically the same thing. So always molarity, make sure the volume's in liters so that everything cancels out correctly. Any questions on that there? Yeah. Now, when we do have a solution that dissolves, if we have something like a 1 molar solution of sodium chloride, that basically means we have 1 mole of solid sodium chloride is dissolved in water, and that will give us basically 1 mole of sodium ions and 1 mole chloride ions. So sometimes we're interested in not necessarily the molarity of the entire, say, ionic compound, but we may actually be interested in the molarity of an individual ions that are floating around in the solution. And we could actually use the molarity of the whole compound to figure out what the molarity of the individual ions are in solution. So for example, if we take a look at sort of how ion concentration works, let's say we had 1 molar sodium chloride solution. And basically in this case, the sodium chloride, when it goes for a swim, because it's a strong electrolyte, is going to completely break apart into sodium ions floating around and chloride ions basically floating around in that solution. And if we were interested, for example, in the sodium's concentration of those ions or the concentration of the chloride ions, we could use the molarity of the whole thing and actually do kind of like a stoichiometry move. This is a 1-to-1 relationship between the whole thing and the sodium ions, which means to get the concentration of the sodium ions, we take 1 times 1 molar, would mean that this solution is 1 molar sodium ions basically floating around. We could also do the same thing for the chloride ions. It is a 1-to-1 relationship here between those two. And that means we could take 1 times our 1 molar, and it would tell us we have 1 molar of chloride ions floating around. So if we were to dissolve some sodium chloride in there, we basically get a 1-to-1 relationship. They basically have the same concentration as the whole thing as they're floating around. Now that does change. For example, if I took 1 molar calcium chloride and a 1 molar calcium chloride, when it breaks apart in solution, the calcium chloride will break apart into a calcium ion and 2 chloride ions. So if this guy is 1 molar, we could still do it for our calcium, a 1-to-1 relationship. And basically for the calcium ion, it would be 1 times 1, which is 1 molar calcium ions floating around. But when we do our whole thing to our chloride, it is a 1-to-2 relationship, which means the concentration of the chloride ions would be 2 times 1 molar, which would be, it is actually 2 molar chloride ions that are floating around in that solution. And if you just take a beaker view of it, if you took some calcium chloride, when that goes in, you get a calcium ion and 2 chloride ions floating around. It is basically twice as concentrated in chloride as it is in calcium. And that's what we see with the concentration. 1 molar for our calcium, 2 molar for our chloride. It's obviously not additive. That is the short way to figure out really quickly what the concentration of an ion is if you know the concentration of the ionic compound. Basically, if it broke apart into a 1 to 3 relationship, you would take the molarity and times it by 3, like we did here, 1 to 2 times it by 2. If it's a 1 to 1 relationship, you don't have to do it. The long version of that calculation is this, just so you see how we get there. You take 1 mole per liter of calcium chloride, and you basically do, like I mentioned before, a mole-to-mole relationship. That is a 1 to 1 relationship from the equation, just like you were doing stoichiometry. A mole of the whole thing gives me 1 mole of the calcium ions. Those cancel, leaves me with 1 mole per liter of calcium ions, which is 1 molar. How do we get to the other guy? We do the same thing, 1 mole per liter of the whole thing. Then we do our stoichiometry, a 1 to 2 relationship in this case. 2 moles of chloride gives us 1 mole of the whole thing. Moles of the whole thing cancel, gives us 2 moles per liter of chloride ions as well. So that is why we multiply by 1. That is why we multiply by 2, the coefficient, and it works out. So that's really the long version of that calculation. But again, really quickly, you can just multiply by the coefficient, and it'll give you that ion concentration. Any questions on that there? Okay, so let's take a look at some here maybe. All right, so calculate the molarity of a solution that's prepared by dissolving 15.6 grams of KBr and enough water to make 1.25 liters. K is 3910, and obviously BR moles per liter. So we have 15.6 grams of KBr given to us. We do have a volume of 1.25 liters. So clearly here we already have that part of it. So what's left really to sort of calculate is moles, and we can't go moles to grams by using, again, our molar mass, right, from the periodic table to do so. By the way, although this one was given to you in liters, it is very common that the volume is given to you in milliliters. So that milliliter to liter conversion is used a lot as well with molarity, converting one way or the other. So in this case, basically, I think we just need to add these guys together, and that's going to give us 119 grams per mole. And we'll use as our conversion factor here to convert our grams into moles. We'll divide by the 119 so that the grams cancel, moles up on top. Grams go away, a little 15.6 divided by 119. Looks like 0.131 moles. That now is the top part that we need. So to figure out our molarity here, it would be our moles, 0.131, divided by our volume in liters, which it already is. And that's going to get us here, it's like 0.105. Now, again, these units do not cancel, so the number always stays with the moles part. It's always per 1 liter of KBr. At this point, you could also convert it back to that big M and just write big M KBr as well. Yep. Any questions on that one there? All right, let's try one more here to wrap it up, I think. What is the mass in grams of sodium nitrate that's needed to make a 2.5 liter solution that has a molarity of 0.15 molar sodium nitrate? Sodium is 2299. Nitrogen is 1401. Okay, so let's take a look. So clearly we're doing something with molarity, which is moles per liter. We are given a volume of 2.5 liters. We are given the molarity here, 0.15 molar. So if you're not sure, we definitely have molarity given to us. We do have volume. So moles would make sense. We are looking for the grams of sodium nitrate. And that also makes sense because Once we have the moles, again, we can use our molar mass here to go from moles to grams, again, from the periodic table. Now, again, you could plug and chug into here and rearrange this, and moles would equal liters times molarity. I am, again, going to kind of use my molarity here as a conversion factor and take more of a dimensional analysis approach. So what that means is 0.150 moles per liter of sodium nitrate is one way we could do it. We could also flip it around, put the liters on top and the moles on the bottom. So once again, just by doing this, it kind of takes away this rearranging and making sure you did it right or not. I could just use my volume here. And again, all I have to remember is opposites cancel, which means that is what I need to do that. Liters are going to cancel, and I know because I did dimensional analysis, are going to multiply and again divide. And that is going to get me here 2.5 times 0.15, 0.375 moles of sodium nitrate. Now that's close to what I need, but I do want grams. So again, to the periodic table here, and I got 22.99 for my sodium. I got 1 nitrogen of 1401, and I got 3 oxygens, each at 16 in this case. That's going to give me 85, I think, grams per mole. Remember, we're going to use that as a conversion factor here. Moles need to go on the bottom, 85 grams up on top, so that everything cancels out correctly there. And we'll go 85 on it. About 31.9 grams of sodium nitrate. Any question on the calculation there? What that number represents is obviously if I wanted to make the solution, I would need to weigh out about 31.9 grams of sodium nitrate. Since it is ionic, probably water is a great solvent, so I could use some water, deionized water probably to dissolve it. I would use enough water to get to a total volume of 2.5 liters, and I would mix it up really good. And at that point, what I should have sitting in front of me is 2.5 liters of a solution that has that molarity of 0.15 molar. Any questions on that there? All right, we're going to lay it up